Hello and welcome to another gentle journey through the mathematical universe. I'm delighted you've joined me tonight wherever you might be resting your head. Perhaps you're nestled in a comfortable chair by a window, watching the evening light fade into darkness. Or maybe you're tucked beneath warm blankets as the world outside grows quiet. Take a moment to notice the temperature of the air around you, the softness of your pillow, the way shadows play across the walls as the day surrenders to night. Wherever you are in this vast world, I hope this exploration of numbers and patterns will serve as a soothing companion as you prepare for sleep. Tonight we're going to wander through one of the most beautiful and mysterious patterns in mathematics, one that emerges when we plot prime numbers in a way that might seem completely arbitrary at first glance. We'll discover spirals that appear like distant galaxies, straight lines that stretch toward infinity, and hidden connections between the most fundamental numbers in mathematics and the elegant curves of the natural world. It's a story that begins with simple curiosity and ends with profound mathematical theorems that have shaped our understanding of how numbers behave. Along the way, we'll encounter ancient mathematicians and modern computer scientists, rational approximations that astounded civilizations, and visual patterns so beautiful they seem almost too perfect to arise from the chaotic world of prime numbers. Before we begin this mathematical adventure, I should mention that this exploration is purely for the joy of discovery and the quiet satisfaction of understanding. Like watching clouds drift across the evening sky or listening to rain against the window, mathematics at its best offers a peaceful contemplation of patterns that exist beyond our everyday concerns. Tonight's journey will take us through concepts that have puzzled and delighted mathematicians for centuries, from the ancient Greeks who first wondered about the nature of prime numbers to contemporary researchers using supercomputers to explore the furthest reaches of number theory. So settle in, let your breathing slow, and prepare to see numbers in a way you've never imagined before. Our story begins not with grand mathematical theories, but with something wonderfully simple: a curious person playing with data on a computer screen, somewhere in the vast landscape of the internet. On a forum called MathStack Exchange, a user known by the name Dweemark posted a question that would reveal one of the most beautiful visual patterns in all of mathematics. They had been experimenting with plotting prime numbers using polar coordinates, a system for describing points in space that uses distance and angle rather than the familiar x and y coordinates we learned in school. This coordinate system, developed by mathematicians in the 17th century, provides a natural way to describe circular and spiral patterns, making it particularly well suited for revealing the hidden periodicities that lurk within seemingly random sequences. The beauty of polar coordinates lies in their intuitive connection to the way we naturally think about position and direction. Instead of saying that something is 3 steps east and 4 steps north, we can say it's 5 steps away in a direction that's 53 degrees north of east. This system proves especially powerful when dealing with phenomena that have natural rotational symmetry, from the orbits of planets to the spiral arms of galaxies to the mathematical patterns we're about to explore. When Dweemark chose to use polar coordinates for plotting prime numbers, they were unknowingly selecting the perfect mathematical lens for revealing patterns that had been hidden in plain sight for thousands of years. To understand what they discovered, imagine yourself standing at the center of a large empty field at twilight, perhaps in the countryside where the air is still and the horizon stretches endlessly in all directions. Instead of describing where objects are by saying they're so many steps east and so many steps north, polar coordinates tell us to walk a certain distance in a specific direction. The first number tells us how far to walk from our starting point, and the second tells us which direction to face, measured as an angle from due east. When we measure these angles in radians, a mathematical unit that connects directly to the geometry of circles, a full circle around is exactly 2 pi radians, which means that pi radians takes us halfway around, and each radian is about 57.3 degrees if you prefer to think in those familiar terms. The choice to use radians rather than degrees is not merely conventional but deeply meaningful. Radians measure angles in terms of the arc length on a unit circle, creating a natural harmony between linear and angular measurements. When an angle is measured as 1 radian, the arc it subtends on a circle of radius 1 has length exactly 1. This elegant relationship between angle and arc length makes radians the natural choice for mathematical analysis, and it will prove crucial to understanding why certain rational approximations to pi create such spectacular visual patterns in our prime number spirals. What Dweemark did was take each prime number and use it twice, once for the distance to walk and once for the direction to turn. So for the prime number 2, they would walk 2 units away from the center and turn through an angle of 2 radians. For the prime 3, they'd walk 3 units and turn 3 radians. For 5, walk 5 units and turn 5 radians, and so on. Each prime number became a single point in this polar coordinate system, creating what mathematicians call a scatter plot, though this one would prove to be far more interesting than most. The decision to use each prime number both as radius and angle might seem arbitrary, but it creates a perfect mathematical microscope for examining the subtle patterns hidden within the prime sequence. At first glance, the result looked chaotic, which is exactly what you might expect from any attempt to visualize prime numbers. Prime numbers are famous for their seemingly random behavior, appearing to follow no obvious pattern as they march through the integers like an irregular drumbeat, echoing through mathematical space. Sometimes they cluster together in intimate groups, like the consecutive primes 11, 13, 17, and 19, creating what mathematicians call prime constellations. Other times they spread far apart, leaving vast deserts of composite numbers that stretch for hundreds or thousands of integers without a single prime to break the monotony. This apparent randomness has fascinated mathematicians for over 2 millennia, ever since Euclid proved that there are infinitely many primes and began the long quest to understand their distribution. If someone asked you to predict where the next prime number would appear after examining the first 1,000 or million primes, you'd find it nearly impossible, even with all the computing power in the world. The gaps between consecutive primes seem to follow no discernible pattern, sometimes being as small as 2, as in twin primes like 11 and 13, and sometimes growing arbitrarily large. This apparent randomness has guarded some of mathematics' deepest secrets, and continues to challenge the most sophisticated mathematical minds. But as Dweemark zoomed out from their scatter plot, something extraordinary began to emerge from the chaos, like constellations becoming visible as our eyes adjust to the darkness of a clear night sky. The seemingly random points started to organize themselves into distinct spiral arms, graceful curves that swept outward from the center with mathematical precision, reminiscent of the majestic spiral galaxies photographed by the Hubble telescope. These weren't vague, barely perceptible patterns that might have been tricks of the eye or wishful thinking projected onto random data. They were clear, unmistakable spirals that emerged with startling clarity as more and more prime numbers were included in the plot. Each spiral arm seemed to carry its own stream of prime numbers into the infinite darkness of the coordinate plane, like rivers of light flowing outward from some central mathematical sun. The curves possessed an organic beauty that seemed almost biological, as if prime numbers were following some hidden genetic code that guided their growth into these elegant forms. As the zoom level increased to include hundreds, then thousands, then tens of thousands of prime numbers, the spiral structure became increasingly clear and increasingly beautiful, revealing layer upon layer of mathematical organization hidden within what had appeared to be pure chaos. Even more mysteriously, some of the spiral arms appeared to be missing entirely, creating gaps in the pattern like teeth missing from a cosmic comb. These weren't random absences but systematic gaps that appeared with mathematical regularity, as if some invisible sieve was filtering out prime numbers from certain directions while allowing them to flow freely in others. The missing arms created a sense of asymmetry and incompleteness that was both puzzling and aesthetically striking, like looking at a garden where certain flower beds had been left deliberately empty according to some hidden design principle. As the view zoomed out further, the spirals themselves began to transform into something even more surprising, perfectly straight lines radiating outward from the center like spokes on an enormous wheel, or rays of light emanating from a brilliant star. These rays seemed to come mostly in groups of 4, creating what looked like a stylized compass rose repeated multiple times across the polar plane. However, occasionally there would be a gap where a ray should have been, as if some invisible hand had erased random spokes from the pattern, leaving behind a cosmic comb with missing teeth that spoke to some deeper mathematical truth about the nature of prime numbers. The beauty of the pattern was undeniable, but its existence posed a profound puzzle that would lead us deep into the heart of number theory. Why would prime numbers, those most fundamental and seemingly chaotic building blocks of arithmetic, arrange themselves into such orderly geometric patterns? What hidden force was organizing them into spirals and rays? What mathematical principles could explain the systematic gaps and the precise groupings? And why did the specific numbers 20 and 280 keep appearing when mathematicians counted the spirals and rays respectively? The questions multiplied like the prime numbers themselves, each answer revealing new mysteries waiting to be explored, new connections waiting to be discovered. Before we dive deeper into this mathematical mystery, Let's take a moment to understand exactly what's being plotted, because everything that follows depends on grasping this fundamental concept with perfect clarity. Think of each step in our sequence as the movement of a very unusual clock hand that behaves quite differently from the familiar timepieces we know. Unlike a regular clock where the hands move at constant speeds and return to their starting positions at regular intervals, this mathematical clock hand grows longer with each tick while simultaneously rotating through a fixed angle. With each tick of this mathematical clock, the hand rotates by exactly 1 radian, which is slightly less than 1/6 of a full rotation, specifically about 57.3 degrees, and simultaneously grows longer by exactly 1 unit. This creates a motion that's part rotation and part radial expansion, like watching a flower bloom while simultaneously spinning slowly in a gentle breeze. The combination of these two motions, the steady angular progression and the steady radial growth, creates the fundamental spiral pattern that underlies all the more complex structures we'll explore. If we were plotting all the whole numbers instead of just the primes, following this rule religiously from the very beginning, we'd see the point 1 Balaban positioned 1 unit away from the center at an angle of 1 radian. Since 1 radian is about 57 degrees, this first point would be located in the first quadrant about 2/3 of the way from the positive x-axis to the positive y-axis. The next point, 2, would be twice as far from the center and rotated through twice the angle, placing it about a 115 degrees from the positive x-axis, well into the second quadrant. Point 3 would be 3 units out, and rotated through 3 radians, which is just slightly less than a half turn since 3 is slightly less than pi. This means the third point would appear in the third quadrant, having completed almost but not quite a half rotation from our starting direction. As we continue this process systematically, plotting 4, 5, 4, 5, 6 as in so on, the points trace out a graceful curve known as an Archimedean spiral, named after the ancient Greek mathematician Archimedes, who first studied such curves over 2,000 years ago in his work on spirals. Archimedes was fascinated by the properties of this curve, which he described as being generated by a point moving at constant speed along a line while that line rotates at constant angular velocity about a fixed point. He proved many beautiful geometric properties of this spiral, including methods for calculating the area enclosed by its arms and the length of the curve itself. The Archimedean spiral appears frequently in nature, from the arrangement of seeds in a sunflower head to the shape of certain seashells to the arms of spiral galaxies, making it one of the most fundamental and recognizable patterns in both mathematics and the natural world. Now, when we make the seemingly arbitrary decision to plot only the prime numbers, removing all the composite numbers from our spiral, the pattern initially looks quite random and chaotic. After all, we're taking a smooth, predictable curve generated by a simple mathematical rule and punching holes in it at seemingly random intervals, keeping only those points whose coordinates happen to be prime numbers. It's like looking at a string of holiday lights where someone has randomly removed most of the bulbs according to some mysterious pattern, leaving only a scattered few to mark the original spiral structure. The process of filtering for primes transforms our smooth Archimedean spiral into something that looks more like a sparse constellation of points scattered across the polar plane. Without the visual continuity provided by the composite numbers, the underlying spiral structure becomes invisible to the naked eye, hidden beneath the apparent randomness of the prime distribution. At small scales, when we can see only the first few dozen prime points, there's no obvious pattern at all, just a seemingly random collection of dots that could have been placed by throwing darts at a coordinate plane. But mathematics has a way of revealing hidden order within apparent chaos, and as we zoom out to see more and more prime numbers, something magical begins to happen. The scattered points begin to organize themselves in ways that seem almost supernatural, as if the prime numbers have been secretly collaborating all along, following some hidden choreography that only becomes visible when we step back far enough to see the grand design. It's reminiscent of those hidden picture puzzles where a random pattern of dots suddenly resolves into a clear image when viewed from the right distance. The individual points merge into smooth curves, and what emerges are those beautiful galactic spirals we glimpsed earlier. These spiral patterns possess a mathematical precision and aesthetic beauty that seems almost too perfect to arise from the chaotic world of prime numbers. The spirals sweep outward with grace and symmetry, each arm carrying its cargo of primes toward infinity with the inevitability of a river flowing toward the sea. The transformation from chaos to order, from randomness to pattern, exemplifies one of the most profound truths in mathematics, that even the most apparently random sequences often contain deep, underlying structures that reveal themselves only when we learn to look at them from the right perspective. This phenomenon hints at one of the most beautiful aspects of mathematical discovery, The way that changing our perspective, choosing the right coordinate system, or the right way of visualizing data, can suddenly illuminate patterns that were invisible before. The prime numbers didn't change when Dwemer decided to plot them in polar coordinates. They remained the same sequence they had always been, but by choosing the right mathematical lens through which to view them, the hidden organizational principles that had been there all along suddenly became visible, transforming chaos into beauty and revealing the deep mathematical structures that govern the distribution of these fundamental numbers. To understand why these spirals appear with such clarity and precision, we need to examine what happens when we plot all the whole numbers, not just the primes. This simpler case will give us the key to unlocking the mystery of the prime spirals, like studying the structure of a building by first examining its underlying framework. When we zoom out far enough to see the pattern formed by all integers plotted according to our numeral and polar coordinates, we discover something remarkable. The points organize themselves into distinct spiral arms, each one containing numbers that share a particular mathematical relationship. The mathematical principle behind this organization is both elegant and profound. As we move through the sequence of positive integers, we're essentially walking along an Archimedean spiral at a steady pace, with each step taking us 1 unit farther from the center and rotating us through 1 additional radian. The key insight is that because 2 pi is an irrational number, approximately 6, 283 180, we never return exactly to our starting direction no matter how many steps we take. However, we can come arbitrarily close to returning to our starting direction, and these near returns create the spiral arm structure we observe. Let's focus on the spirals that emerge when we can count exactly 6 arms in the pattern, a scale that provides an excellent starting point for understanding the mechanism behind all the larger patterns we'll encounter. At this level of magnification, we can clearly see 6 distinct spiral arms, each one containing numbers that share a specific mathematical property. Notice how all the multiples of 6 form one arm of the spiral, the points 6, 6, 12, 12, 18, 18, 24, 24, and so on, creating a smooth curve that spirals outward with mathematical precision. The next spiral arm contains all the numbers that are one more than a multiple of 6, the points 1, 1, 7, 7, 13, 13, 19, 19, and so forth. These numbers belong to what mathematicians call the residue class 1 modulo 6, meaning they all leave a remainder of 1 when divided by 6. The third arm holds all numbers that are 2 more than a multiple of 6, the residue class 2 modulo 6, including points like 2, 8, 8, 14, 14, 20, 20. This pattern continues systematically until we've accounted for all 6 possible remainders when dividing by 6. The mathematical reason for this organization is beautifully simple and relates to the fundamental nature of circular motion and the relationship between radians and degrees. Remember that each step forward in our sequence involves rotating by exactly 1 radian. When we count up by 6, we've rotated through a total of 6 radians, which is just slightly less than 2 pi radians, approximately 6, 283 180. The amount needed for 1 complete rotation around the circle. Since 6 2 pi, every time we add 6 to our count, we've almost completed a full turn, ending up just slightly short of where we started. This near completion of a full rotation is the key to understanding the spiral structure. After 6 steps, we're at angle 6 radians, which is about 303.338 degrees, just 16.2 degrees short of a complete 360-degree rotation. After another 6 steps, we're at angle 12 radians, which is about 60.87.5 degrees, or 327.5 degrees if we subtract 1 complete rotation. This means we're now only 302.5 degrees away from completing 2 full rotations. Each group of 6 steps brings us progressively closer to completing an exact number of rotations, creating a slow spiral that gradually winds outward. Another 6 steps brings us even closer to completing a 3rd full rotation, but still just a tiny bit short. 6 more steps and we're slightly closer still to completing 4 rotations. This gentle progression where each group of 6 steps brings us almost but not quite back to where we started directionally, creates the illusion of a smooth curved line spiraling slowly outward. It's like walking in a circle that's just slightly incomplete, so that each lap brings you to a position just a little different from where you started the previous lap, gradually spiraling outward like the groove on a vinyl record. The precision of this near return depends on how close 6 is to 2 pi. Since 6 is 0.95 toes 2 pi, we complete about 95.4% of a full rotation with each group of 6 steps. The remaining 6% creates the slow spiral motion that makes the 6 residue classes appear as distinct arms. If 6 were exactly equal to 2 pi, all multiples of 6 would land at exactly the same angle, creating a straight line radiating from the origin rather than a spiral. If 6 were much farther from 2 pi, the spiral would wind much more quickly, and the arm structure would be less apparent. When we restrict our view to include only prime numbers, most of these spiral arms disappear entirely, and for reasons that become crystal clear once we think about the fundamental properties of primes and their relationship to divisibility. A prime number greater than 2 cannot be a multiple of 6, since all such numbers are divisible by both 2 and 3, making them composite by definition. This immediately eliminates one of the 6 spiral arms from our prime number plot, leaving us with at most 5 arms to consider. Similarly, no prime except 2 itself can be 2 or 4 positions away from a multiple of 6, since all such numbers are even and therefore divisible by 2. The numbers that are 2 more than a multiple of 6 include 2, 8, 14, 20, 26, and so on. Apart from 2 itself, all of these are even and therefore composite. The same logic applies to numbers that are 4 more than a multiple of 6. They include 4, 10, 16, 22, 28, and so on, all of which, except for the impossible case of 4 being prime, are even and therefore composite, and no prime except 3 itself can be 3 positions away from a multiple of 6, since all such numbers are divisible by 3. The numbers in this residue class include 3, 9, 15, 21, 27, and so on. Apart from 3 itself, every number in this sequence is a multiple of 3 greater than 3, making it composite by definition. This eliminates 3 more spiral arms from our prime number visualization, leaving us with only 2 arms visible when we filter for primes. This leaves only 2 spiral arms visible when we filter for primes, those containing numbers that are 1 more than a multiple of 6, and those containing numbers that are 5 more than a multiple of 6. In mathematical language, this means that all prime numbers greater than 3 belong to exactly one of 2 residue classes modulo 6. These are the residue classes 1 and 5 modulo 6, corresponding to numbers of the form 6k pol 1 and 6k pol 5 respectively, where k is any non-negative integer. The fact that all primes greater than 3 must be of the form 6k pol 1 is one of the first non-trivial facts that students learn about prime numbers, and it illustrates beautifully how the constraints of divisibility shape the possible locations where primes can appear. This result follows immediately from the observation that any integer can be written in exactly one of 6 forms: 6k, 6k pol 1, 6k pol 2, 6k pol 3, 6k pol 4. Since 6k is divisible by 6, 6k pol 2 and 6k pol 4 are divisible by 2 and 6k pol 3 is divisible by 3, only the forms 6k pol 1 and 6k pol 5 can potentially be prime along with the special cases 2 and 3. The term residue class might sound unnecessarily complicated, but it's actually quite useful for describing the patterns we're observing. A residue class modulo n is simply the set of all integers that leave the same remainder when divided by n. The word residue is a somewhat overdramatic way of saying remainder, and modulo n indicates that n is the number we're dividing by, so the residue class 1 modulo 6 consists of all numbers that leave remainder 1 when divided by 6, 1, 7, 13, 19, 25, 31. This terminology, while perhaps sounding pretentious at first, becomes genuinely useful when discussing the patterns we're observing. Each spiral arm corresponds to a different residue class, and the reason we can see them as distinct spirals is that 6 radians is very close to 2 pi radians, making 6 steps nearly equivalent to 1 complete rotation. The reason only 2 arms remain visible when we filter for primes is that prime numbers can only belong to 2 of the 6 possible residue classes modulo 6, with the rare exceptions of the primes 2 and 3 themselves. Now that we understand the basic mechanism behind the 6-armed spirals, we can scale up our thinking to understand the more complex and spectacular patterns that emerge at larger scales. The same principle that creates 6 spiral arms when 6 radians is close to a full rotation can create many more arms when we find larger numbers that are close to whole multiples of 2 pi radians. And as it turns out, number theory provides us with some remarkably precise approximations, leading to spiral patterns so tight they appear almost like straight lines radiating from the origin. Consider what happens when we take 44 steps in our polar coordinate dance, a number that might seem arbitrary but actually has deep mathematical significance. After rotating through 44 radians, we've completed 44 2 pi rotations, which works out to be approximately 7,028 full rotations. This means we've made just slightly more than exactly 7 complete turns, ending up very close to where we would have been after exactly 7 rotations. The precision of this approximation is remarkable. We overshoot the target by only about 0.28% of a full rotation. This near-perfect alignment means that when we count by multiples of 44, each point lands almost exactly on top of the previous one when we account for the completed rotations just slightly farther out due to the increasing radius. The point 4444 lies almost exactly along the same ray from the origin as the point 0 Toro 2 would if it existed, just 44 units farther out. The point 88 Saint 88 lies almost exactly along the same ray as both of these, just 88 units from the origin. This creates what appears to be a single, very tight spiral arm containing all multiples of 44. Similarly, all numbers that are one more than a multiple of 44 form another tight spiro, rotated 1 radian counterclockwise from the first. The points 1, 45 and 45, 89, 89 and so on lie very close to the same ray from the origin, creating another nearly straight line. Numbers that are 2 more than a multiple of 44 form a third spiro, numbers that are 3 more form a fourth, and so on until we have 44 distinct spiral arms, each one so tightly wound that they appear almost like straight lines radiating from the center. The mathematical foundation for this pattern lies in one of the most famous rational approximations to pi in the history of mathematics. The fact that 44 radians is very close to 7 complete rotations is equivalent to saying that 4447 is a very close approximation to 2 pi, or equivalently that 22a7 is a very close approximation to pi. This fraction 22a7 1/4 approximates pi 45d Saint 3 with an error of only about 0.04%, making it accurate to better than 1 part in 200 and 500. The approximation 22a7 for pi is one of the most ancient and well-known in mathematics, used by civilizations from the Babylonians to the Chinese to the Greek. Archimedes himself used this approximation in his calculations, though he was careful to note that it was an upper bound for the true value of pi. The fraction appears in countless historical texts and remains useful today for quick mental calculations when extreme precision isn't required. A circle with diameter 7 units has circumference very close to 22 units, making this approximation both memorable and practical. The reason this approximation creates such clear spiral structure in our polar plot is that it means 44 steps or any multiple of 44 steps brings us very close to an integer number of complete rotations. The small discrepancy between 44.7 and the true value of 2 pi creates a very slow drift in angle as we move through the residue classes, modulo 44, resulting in spiral arms so tightly wound they're barely distinguishable from straight lines. When we filter this 44-armed pattern to show only prime numbers, many of the spiral arms disappear entirely, and for the same fundamental reasons we saw in the simpler 6-armed case. The disappearance follows predictable patterns based on the divisibility properties of numbers in different residue classes. Prime numbers cannot appear in spiral arms corresponding to even residue classes, since all such numbers would be even and therefore not prime except for 2 itself. This immediately eliminates half of the 44 spiral arms. Similarly, primes cannot appear in residue classes that are multiples of 11, since all such numbers would be divisible by 11 and therefore not prime except for 11 itself. Since 44 race say mean 4 cois 11, every 11th residue class starting from 0 corresponds to multiples of 11. The classes 0, 11, 22 and 33 modulo 44. These 4 classes must be eliminated from our prime visualization, along with all the even classes. The systematic elimination of residue classes follows a precise mathematical pattern determined by the prime factorization of 44. Since 44a2 Coro Toes 11, a number can be prime only if it shares no common factors with 44 other than 1. This means it cannot be divisible by 2 or by 11. The residue classes modulo 44 that can potentially contain prime numbers are precisely those that are not divisible by 2 or 11. The spiral arms that remain visible are precisely those corresponding to residue classes that don't share any common factors with 44. When we count how many such residue classes exist among the numbers from 1 to 44, we're computing what mathematicians call Euler-Totian function, denoted Fourier 44. This function counts how many numbers from 1 to 44 are relatively prime to 44. meaning they share no common factors with 44 other than 1. The calculation of 4a4 follows a beautiful multiplicative formula. Since 44 to 2 cur to dot 11, we have 4a4 to 4 44 to dot 11, tidding. This confirms that exactly 20 of the 44 possible residue classes can contain prime numbers, which explains why we see 20 spiral arms in the prime number pattern at this scale. The remaining 24 residue classes are guaranteed to contain only composite numbers, with the rare exceptions of the primes 2 and 11 themselves. Euler's Totient function, introduced by the great Swiss mathematician Leonhard Euler in the 18th century, is one of the most important functions in number theory. It appears in context ranging from abstract algebra to cryptography to the analysis of algorithms. The function has many beautiful properties, including its multiplicative nature. If m and n are relatively prime, then 4f mn poting. This property makes it possible to compute 4f n efficiently for any positive integer n by factoring n and applying the formula poting. Within each of the 20 remaining spiral arms, something remarkable occurs. The prime numbers appear to be distributed more or less randomly. This observation, which might seem like a minor detail when we're focused on the beautiful geometric patterns, actually points toward one of the most important theorems in all of number theory. The apparent randomness within each arm, combined with the roughly equal distribution of primes among the different arms, suggests a deep and beautiful mathematical truth that took centuries to prove rigorously. This seemingly random distribution within each residue class is not actually random at all, but rather reflects a profound democratic principle that governs how prime numbers distribute themselves among arithmetic progressions. The fact that primes appear with roughly equal frequency in each allowable residue class is a manifestation of a fundamental symmetry in the mathematical universe, one that connects the discrete world of number theory with the continuous world of analysis and the elegant structures of complex function theory. As we zoom out even further from our prime spiral visualization, the pattern transforms once again, revealing an even more precise and spectacular example of the same underlying principle. At the largest scale visible in typical prime spiral plots, we encounter what is arguably one of the most impressive rational approximations in all of mathematical history. The number 710 radians turns out to be extraordinarily close to a whole number of complete rotations, so close that the resulting spiral arms appear virtually indistinguishable from perfectly straight lines even when extended far from the origin. Let's examine just how remarkable this approximation truly is. When we complete 710 steps in our polar coordinate journey, we've rotated through 710 ray 2 pi 112, 9.999 save complete rotations. This means we've made almost exactly 113 complete turns, missing perfect alignment by less than 1 part in 10,000. To put this extraordinary precision in perspective, if we were to make 113 complete rotations and then continue for just 0.0095% of an additional rotation, we would land exactly at the 710 radian mark. In practical terms, this incredible precision means that points separated by 710 steps land almost exactly on top of each other when we account for the completed rotations, creating spiral arms so tightly wound that even very far from the center, they appear to be perfectly straight lines. The visual effect is stunning. What should be a spiral becomes virtually indistinguishable from a collection of rays emanating from the origin, each one extending to infinity with mathematical precision. This extraordinary approximation corresponds to the fraction 355/113, which is one of the most celebrated approximations to pi in the entire history of mathematics. Discovered by the Chinese mathematician Zhu Chengji in the 5th century CE, this fraction approximates pi with an accuracy that is almost unbelievable. 355/113, bat 113, while pi rate 113.9, while pi rate 113.927, giving an error of less than 1 part in 10 million. This level of precision remained unmatched for nearly 1,000 years, and is still more accurate than needed for virtually any practical application. The fraction 355/113 is sometimes called Milo in honor of Zhu Chengji, who computed it using ingenious geometric methods involving regular polygons inscribed in and circumscribed about circles. The calculation required extraordinary patience and computational skill, as Zhu Chengji had to work with polygons having thousands of sides to achieve this level of precision. The result was so accurate that it wasn't surpassed until the development of infinite series representations of pi in the 17th century. The visual impact of this approximation in our prime spiral plot is breathtaking. When we plot all 7 to 10 residue classes modulo 710, we see what appears to be a perfect starburst pattern of straight lines radiating from the center, like a mathematical sunburst or a cosmic firework frozen at the moment of explosion. Each line extends from the origin toward infinity with perfect straightness, creating a pattern of almost crystalline perfection that seems to belong more to the realm of art than mathematics. But when we filter for prime numbers only, removing all the residue classes that must contain only composite numbers, a striking and highly organized pattern emerges from this apparent perfection. The lines don't disappear randomly. Instead, they vanish according to a systematic pattern that reveals the deep mathematical structure underlying the distribution of prime numbers. The systematic nature of these disappearances creates gaps and clusters that encode fundamental information about the arithmetic properties of the number 710 and its relationship to prime numbers. Since 710 ni a2 ties 5 ties 7 to 1, the prime factorization reveals exactly which residue classes can potentially contain prime numbers. A number can be prime only if it shares no common factors with 710 other than 1, which means it cannot be divisible by 2, 5, or 7 to 1. The systematic removal of these forbidden residue classes creates the beautiful pattern of gaps and clusters that we observe in the filtered visualization. When we remove all the even residue classes, we're left with every other ray in what would otherwise be a very crowded pattern. This creates an immediate visual rhythm like the alternating pattern of fence posts and gaps that you might see along a country road. The even spacing of these removals reflects the fundamental fact that apart from 2 itself, all prime numbers must be odd. This simple constraint immediately eliminates half of the 710 possible directions, leaving us with 35 and 55 rays that could potentially contain prime numbers. When we further remove all residue classes divisible by 5, we see that these missing rays are evenly spaced at every 5th position among the remaining rays. Numbers ending in 0 or 5 except for 5 itself cannot be prime, since they're divisible by 5. In our polar coordinate system, this constraint manifests as the systematic removal of rays at regular intervals, creating a pattern reminiscent of the spokes missing from a wheel where every 5th spoke has been removed for structural or aesthetic reasons. Finally, when we remove the residue classes divisible by 7 to 1, we see why the remaining rays often appear in groups of 4 with occasional gaps. Since 7 to 1 is a relatively large prime, there are only a few residue classes modulo 710 that are divisible by 7 to 1. Specifically, these are the classes 0, 7 to 1, 142, 214, 20tt4, 354, 2t6, 4097. When we remove these from our already filtered set of rays, we create the characteristic pattern of clustering that gives the visualization its distinctive appearance. This systematic removal process explains both the grouping pattern we observe and the total count of visible rays. The number of residue classes modulo 710 that can potentially contain prime numbers is given by Euler's Tothian function. 4, 710 ni 710 tos 1, 142 tos 145 tos 147 to 1. 710 tos 142 tos 45 tos 7 to min 7 to 1. This calculation confirms that exactly 280 of the 710 possible directions can contain prime numbers, matching the count of rays visible in the filtered pattern, and explaining the mysterious appearance of this number in prime spiral visualizations. The mathematical beauty of this result extends far beyond the visual pattern it creates. The systematic way that prime numbers avoid certain directions while appearing in others demonstrates a fundamental principle about how primes are distributed among different arithmetic progressions. This observation leads us directly to one of the crown jewels of number theory, Dirichlet's theorem on primes in arithmetic progressions. A result so profound that it revolutionized our understanding of how prime numbers behave in the infinite landscape of integers. But before we explore Dirichlet's groundbreaking theorem, let's take a moment to appreciate the historical context in which these discoveries were made. The systematic study of prime numbers dates back over 2 millennia to ancient Greece, where mathematicians like Euclid and Eratosthenes laid the foundational stones of number theory. Euclid's proof that there are infinitely many primes presented in his Elements around 300 BCE remains one of the most elegant arguments in all of mathematics. Using a brilliant proof by contradiction, Euclid showed that any finite list of primes can be extended by constructing a new prime not on the list. Eratosthenes, working around the same time, developed the famous sieve of Eratosthenes, an algorithm for systematically finding all prime numbers up to a given limit. His method works by starting with all integers from 2 to n, then systematically removing multiples of each prime as they're discovered. The numbers that remain after this sieving process are precisely the primes. This ancient algorithm remains one of the most efficient methods for finding small primes and beautifully illustrates the way that primes hide among the integers. Like gems scattered through ordinary rock, the ancient Greeks were fascinated by the apparent irregularity of prime numbers. They observed that primes sometimes cluster together like 11, 13, 17, 19, and sometimes spread far apart, leaving large gaps filled only with composite numbers. They wondered whether there might be patterns hidden within this apparent chaos, but lacked the mathematical tools to make significant progress on this question. The full power of prime number theory would have to wait for the development of new mathematical techniques over the following 2,000 years. The next major breakthrough came in the 18th century with the work of Leonhard Euler, whose contributions to number theory were as revolutionary as his work in analysis, mechanics, and geometry. Euler introduced the concept of the totient function that we've already encountered, and he proved many fundamental results about the distribution of prime numbers. His work on what would later be called the Riemann zeta function laid the groundwork for connecting the discrete world of number theory with the continuous world of mathematical analysis. Euler's insight was to consider infinite products and series involving prime numbers, treating primes not as isolated objects but as part of interconnected mathematical structures. His famous proof that there are infinitely many primes, different from Euclid's but equally elegant, used the divergence of the harmonic series and properties of the natural logarithm. This approach hinted at deep connections between prime numbers and the continuous functions of calculus, connections that would prove crucial for understanding prime distribution. The 19th century brought even more dramatic advances, culminating in the work of Peter Gustav Lejeune Dirichlet, whose theorem on primes in arithmetic progressions provides the key to understanding our spiral patterns. Dirichlet was born in Germany in 1805 and spent much of his career in Berlin, where he made fundamental contributions to number theory, analysis, and mathematical physics. His work on prime distribution represented a quantum leap in mathematical sophistication, introducing techniques that remain central to analytic number theory today. To understand what Dirichlet's theorem tells us, let's consider a simpler example that most people can relate to directly, one that connects to our everyday experience with numbers. Since we write numbers in base 10, grouping numbers by their last digit is equivalent to grouping them by their residue classes modulo 10. The last digit of a number is simply the remainder when that number is divided by 10. So this familiar concept is actually a special case of the mathematical ideas we've been exploring throughout our journey. When we think about prime numbers and their last digits, some patterns become immediately obvious through simple reasoning about divisibility. Apart from the number 2 itself, no prime can end in an even digit 0, 2, 4, 6, or 8, since any such number would be divisible by 2 and therefore composite. This eliminates half of the possible last digits right away. Similarly, apart from 5 itself, no prime larger than 5 can end in 5, since any such number would be divisible by 5 and therefore composite. This simple analysis leaves only 4 possible last digits for prime numbers, 1, 3, 7, and 9. Any prime number greater than 5 must end in one of these 4 digits. This is one of the first non-trivial facts that students learn about prime numbers, and it provides an excellent introduction to the idea that divisibility constraints limit where primes can appear. But this observation, while useful, only scratches the surface of much deeper patterns. A much more subtle and interesting question emerges: how are the prime numbers distributed among these 4 allowable last digits? If we make a histogram showing what fraction of all primes end in each digit, what pattern do we expect to see? Since there's no obvious reason why primes should prefer one digit over another among the 4 allowable choices, we might guess that they're distributed roughly equally among the 4 possibilities, with about 25% ending in each of the digits 1, 3, 7, and 9. This intuition turns out to be exactly correct, but proving it rigorously is extraordinarily difficult and requires some of the most sophisticated techniques in all of mathematics. As we examine more and more prime numbers, creating larger and larger samples, the distribution does indeed approach perfect equality. About 25% of all primes end in 1, about 25% end in 3, about 25% end in 7, and about 25% end in 9. The fluctuations around these percentages become smaller and smaller as we include more primes in our count, eventually vanishing entirely in the limit of infinite primes. The uniform distribution might seem like a natural consequence of the random behavior of prime numbers, but this interpretation is fundamentally misleading. Prime numbers are not random at all. They form a definite deterministic sequence with deep underlying patterns and structure. The fact that they distribute themselves evenly among allowable residue classes is a remarkable theorem that connects the discrete world of number theory with the continuous world of mathematical analysis, revealing hidden symmetries in the mathematical universe. To make this more concrete, let's imagine conducting an experiment. We'll examine the first million prime numbers and count how many end in each of the digits 1, 3, 7, and 9. If we plot these counts as a histogram, we'll see 4 bars of nearly equal height, each representing close to 250,000 primes. The small differences between the bar heights represent statistical fluctuations that become negligible compared to the total count as we examine more and more primes. If we extend our experiment to the first billion primes, the histogram bars become even more nearly equal in height. The difference between the largest and smallest counts becomes a smaller and smaller fraction of the total number of primes examined. In the mathematical limit of infinitely many primes, the distribution becomes perfectly uniform, with exactly 25% of primes ending in each allowable digit. This uniform distribution is not an accident or a curious coincidence, but rather a manifestation of a fundamental symmetry principle that governs the behavior of prime numbers. The symmetry reflects the fact that from the perspective of divisibility by 10, there's no mathematical reason to prefer one allowable residue class over another. The primes respect this symmetry by distributing themselves as evenly as possible among all available options. Direchlet's theorem, proved in 1837, generalizes this observation to any modulus, not just 10. The theorem states that if we take any positive integer n and any integer a that shares no common factors with n, meaning gzt, an b1, then the arithmetic progression a, ann a pos 2n, aan d1, and the arithmetic progression a, ann d1, contains infinitely many prime numbers. This is already a remarkable result, guaranteeing that primes appear infinitely often in any arithmetic progression that could theoretically contain them. But Dirichlet proved something even stronger and more beautiful. He showed that these primes are distributed among all the allowable arithmetic progressions with equal density. More precisely, if we count all the prime numbers less than some large bound x and ask what fraction of them belong to a particular allowable arithmetic progression, that fraction approaches 1/1 n as x approaches infinity, where first n is Euler's totin function counting the number of residue classes modulo n that can potentially contain prime numbers. This means that prime numbers are distributed as evenly as possible among all the arithmetic progressions that could theoretically contain them. They don't show favoritism toward any particular residue class but instead maintain perfect mathematical democracy, ensuring that each allowable progression receives its fair share of primes in the long run. This democratic principle represents one of the most beautiful examples of mathematical symmetry, showing that the apparent chaos of prime distribution conceals a deep and elegant order. The proof of Dirichlet's theorem is a masterpiece of 19th-century mathematics, combining techniques from number theory, complex analysis, and what was then the cutting-edge field of Fourier analysis. Dirichlet's approach was revolutionary because it was one of the first times that the continuous methods of calculus and complex analysis were successfully applied to problems about discrete objects like prime numbers. This fusion of different mathematical worlds opened up entirely new ways of thinking about number theory. One of the most surprising aspects of Dirichlet's proof is its heavy reliance on complex analysis, the study of functions involving complex numbers. At first glance, this seems bizarre. What could complex numbers possibly have to do with the distribution of prime numbers? After all, primes are among the most concrete and elementary objects in mathematics, while complex numbers involve the mysterious square root of -1 and seem to belong to a much more abstract and ethereal realm. The connection emerges through Dirichlet's brilliant idea to study what are now called Dirichlet L functions, which are complex-valued functions that encode information about how primes distribute among different residue classes. These functions are built using infinite series that involve both prime numbers and complex exponentials, creating a bridge between the discrete world of number theory and the continuous world of complex analysis. By studying the behavior of these L functions, Dirichlet was able to extract precise information about prime distribution. The key insight is that complex analysis provides powerful tools for understanding infinite series and products, tools that are perfectly suited for analyzing the subtle patterns hidden within prime distribution. The techniques of contour integration, residue calculus, and analytic continuation allow mathematicians to extract information that would be impossible to obtain through purely elementary methods. This represents one of the most beautiful examples of mathematical unity, showing how different areas of mathematics illuminate each other in unexpected ways. Dirichlet's theorem has profound implications that extend far beyond the specific question of how primes distribute among arithmetic progressions. The theorem provides the foundation for much of modern analytic number theory and continues to influence contemporary research on prime numbers. Many of the most important open problems in number theory, including the Riemann hypothesis and the twin prime conjecture, can be viewed as attempts to understand finer details of the patterns that Dirichlet first revealed. The techniques that Dirichlet developed to prove his theorem continue to evolve and find new applications. Recent breakthroughs on small gaps between primes, including work by mathematicians like Yitang Zhang and James Maynard, have their roots in Dirichlet's original insights about how primes distribute among residue classes. The methods have been refined and extended, but the fundamental approach of using complex analysis to study prime distribution remains central to the field. The story of these prime spirals also illustrates something profound about the nature of mathematical discovery itself. The original observation that sparked this entire investigation was completely unmotivated from a practical standpoint. There's no inherent reason to plot prime numbers using polar coordinates where both coordinates equal the prime itself. It was pure mathematical play, the kind of curious experimentation that happens when someone with the right tools and the right mindset decides to see what happens when they try something just for the fun of it. Yet this apparently arbitrary exploration led directly to some of the deepest and most important ideas in mathematics. The visual patterns revealed by plotting primes in polar coordinates provide intuitive illustrations of Dirichlet's theorem, rational approximations to pi, Euler's totient function, and the fundamental principles governing how prime numbers distribute themselves among arithmetic progressions. What began as idle curiosity became a window into some of the most profound structures underlying the theory of numbers. This kind of serendipitous discovery is not unusual in mathematics, but rather represents one of its most characteristic features. Many of the most important mathematical insights have emerged from investigations that initially seemed pointless or purely recreational. The key insight is that mathematics is so deeply interconnected that almost any genuine exploration, if pursued with sufficient care and insight, has the potential to uncover important truths. When we play with mathematical ideas in creative ways, we often stumble upon connections that reveal new perspectives on old problems. The interconnectedness of mathematics means that what appears to be an arbitrary question often turns out to connect with fundamental mathematical structures. The fact that a random data visualization experiment reveals patterns related to Dirichlet's theorem is not a coincidence but rather a reflection of the underlying unity of mathematical truth. Deep mathematical concepts have a way of manifesting themselves in unexpected places, revealing the hidden order that underlies the apparent chaos of complex systems. This unity extends far beyond number theory to encompass virtually every area of mathematics. The same rational approximations to pi that create beautiful spiral patterns in prime plots also appear in the analysis of planetary motion, the design of mechanical systems, and the study of wave phenomena. Euler's totient function, which counts allowable residue classes for prime distribution, also plays crucial roles in cryptography, abstract algebra, and computer science. The complex analysis techniques used in Dirichlet's proof find applications in physics, engineering, and mathematical biology. Let's explore some of these unexpected connections to see how the ideas we've been discussing tonight extend into other areas of mathematics and science. The rational approximation 355-113 for pi, which creates the spectacular straight-line patterns in our prime spirals, has a fascinating history in astronomy and navigation. Ancient and medieval astronomers used this approximation to calculate planetary positions and predict eclipses with remarkable accuracy, despite having no knowledge of its connection to prime number distribution. The Chinese mathematician Zhu Chongji, who first computed this approximation in the 5th century, was primarily interested in calendar reform and astronomical calculations. He had no way of knowing that his fraction would later illuminate patterns in prime numbers that wouldn't be discovered for another 15 centuries. This illustrates beautifully how mathematical truths transcend their original contexts, finding new applications and revealing new facets of their beauty as mathematics evolves and expands. The approximation 22.7 for pi has an even longer and more diverse history. It appears in ancient Babylonian, Egyptian, and Indian mathematical texts, where it was used for practical calculations involving circles and spheres. Medieval Islamic mathematicians used it in their architectural designs, creating the beautiful geometric patterns that adorn mosques and palaces throughout the Islamic world. Renaissance artists and engineers employed it in their studies of perspective and mechanical design. Today, these same approximations find applications in modern technology. Computer graphics algorithms use rational approximations to pi for efficient rendering of circular and spherical objects. Digital signal processing relies on these approximations for implementing trigonometric functions in microprocessors. Even modern cryptographic systems, which depend heavily on number-theoretic concepts like Euler's totient function, can trace their mathematical lineage back to the same ideas that create patterns in our prime spirals. The visual patterns we've explored also connect to the broader study of mathematical visualization and the role of visual thinking in mathematical discovery. Throughout history, mathematicians have relied on geometric intuition and visual representations to guide their theoretical investigations. The ancient Greeks thought of numbers geometrically, representing them as arrangements of points or as lengths and areas. This geometric perspective led to many of their most important discoveries about prime numbers and divisibility. During the Renaissance, the development of perspective in art coincided with advances in mathematical understanding of geometric projection and coordinate systems. Artists like Leonardo da Vinci and Albrecht Dürer were also serious mathematicians who contributed to our understanding of geometric relationships. Their work on perspective and proportion laid foundations that would later support the development of analytic geometry and calculus. The 19th and 20th centuries saw an explosion of interest in mathematical visualization, driven partly by advances in printing technology that made it possible to reproduce complex diagrams and graphs. Mathematicians like Felix Klein and David Hilbert emphasized the importance of geometric intuition in mathematical research, arguing that visual thinking often provides the key insights needed to solve difficult problems. The development of computer graphics in the late 20th century opened up entirely new possibilities for mathematical visualization. Today's prime spiral visualizations represent a continuation of this ancient tradition of using visual representations to illuminate mathematical structures. The computer-generated images that reveal galactic spirals and radiating rays in prime distributions are direct descendants of the geometric diagrams that ancient mathematicians drew in sand or carved in stone. The tools have changed dramatically, but the fundamental human desire to see and understand mathematical patterns remains constant. This brings us to consider the psychological and cognitive aspects of mathematical pattern recognition. Humans seem to have an innate ability to detect patterns and regularities, an ability that has obvious evolutionary advantages for survival and navigation. This pattern recognition capability, originally developed for interpreting natural environments and social situations, proves remarkably well suited for mathematical exploration and discovery. The fact that we find mathematical patterns beautiful suggests deep connections between our aesthetic sensibilities and our logical reasoning abilities. The same mental processes that allow us to appreciate the beauty of a sunset or a piece of music also enable us to recognize the elegance of a mathematical proof or the beauty of a geometric pattern. This aesthetic dimension of mathematics is not merely decorative but plays a crucial role in mathematical discovery and understanding. When we look at the spiral patterns created by prime numbers, we're engaging multiple cognitive systems simultaneously. Our visual processing systems detect the spiral shapes and radial symmetries. Our pattern recognition systems identify the regularities and systematic structures. Our aesthetic sensibilities respond to the beauty and elegance of the patterns, and our logical reasoning systems work to understand the mathematical principles that create these patterns. This multi-layered cognitive engagement helps explain why visual representations can be so powerful for mathematical understanding. They don't just illustrate abstract concepts, they engage our minds at multiple levels, creating rich networks of association and understanding that pure symbolic manipulation might not achieve. The spiral patterns in prime plots don't just show us facts about Dirichlet's theorem, they help us feel and internalize these mathematical truths in ways that purely analytical approaches might not accomplish. The study of prime spirals also connects to broader questions about the relationship between order and chaos in mathematical and natural systems. The apparent randomness of prime distribution at small scales gives way to beautiful regular patterns at larger scales, illustrating how complex systems often exhibit different types of behavior at different levels of observation. This phenomenon appears throughout mathematics and science, from the seemingly random motion of gas molecules that creates predictable thermodynamic behavior to the chaotic dynamics of individual neurons that somehow produce coherent thought and consciousness. In the case of prime numbers, the chaos at small scales is not truly random, but reflects the complex interplay of multiple arithmetic constraints. Individual primes may appear at unpredictable locations, but their collective behavior follows precise statistical laws that emerge from the deeper mathematical structures we've been exploring. This represents a profound example of how mathematical determinism can produce apparent randomness, and how apparent randomness can conceal deeper deterministic patterns. The mathematical tools needed to understand these multi-scale phenomena often require sophisticated techniques that bridge different areas of mathematics. In the case of prime distribution, we need number theory to understand the basic arithmetic constraints, complex analysis to study the analytic properties of L functions, harmonic analysis to understand the Fourier theoretic aspects of the problem, and probability theory to interpret the statistical patterns that emerge. This multidisciplinary approach reflects the increasing interconnectedness of modern mathematics. As we continue our exploration of prime spirals, it's worth considering how these patterns might connect to other areas of mathematics and science. The spiral forms that emerge from prime plots bear striking resemblances to spiral patterns found throughout the natural world. From the arrangement of seeds in sunflower heads to the shapes of nautilus shells to the arms of spiral galaxies, while these resemblances might be purely coincidental, they raise interesting questions about whether similar mathematical principles might govern both prime distribution and natural pattern formation. The Fibonacci sequence, which appears in many natural spiral patterns, has its own fascinating connections to number theory and prime distribution. The ratios of consecutive Fibonacci numbers approach the golden ratio Foubs-C1 Fourier-Pro2, which is one of the most famous irrational numbers in mathematics. The continued fraction expansion of Foubs has particularly simple structure, which gives it unusual properties in the theory of rational approximations. These properties make Foubs especially resistant to good rational approximations, in contrast to pi, which admits excellent approximations like 300π. The difference between pi and Foubs in terms of rational approximability reflects deep differences in their arithmetic properties. The number pi is what mathematicians call a normal transcendental number, meaning it has no special arithmetic relationships with rational numbers beyond the obvious ones. The golden ratio Foubs, on the other hand, is an algebraic number, specifically a root of x cur, x1, 1, with special properties that make it badly approximable by rationals. These different approximation properties would produce very different spiral patterns if we were to plot sequences using Foubs instead of pi. The poor rational approximations to Foubs would prevent the formation of the tight spiral arms that we see in prime plots, instead producing patterns that maintain their spiral character at all scales. This illustrates how the specific arithmetic properties of fundamental constants directly influence the visual patterns that emerge from mathematical visualizations. The connection between rational approximations and visual patterns extends far beyond prime spirals to encompass many other areas of mathematical visualization. Whenever we have a sequence of points that involves rotation by an irrational angle, the quality of rational approximations to that angle determines the large-scale structure of the resulting pattern. This principle appears in studies of quasicrystals in physics, in the analysis of planetary motion in astronomy, and in the design of algorithms for computer graphics. The mathematical theory of continued fractions provides the systematic framework for understanding rational approximations and their quality. Every real number has a unique representation as a continued fraction, and the convergence of this continued fraction provide the sequence of best rational approximations to the number. For pi, the continued fraction expansion begins 3, 7, 15, 1, 29, 2, 1, 1. Where the large number 29.2 corresponds to the exceptionally good approximation 3.5. The structure of continued fraction expansions encodes deep information about the arithmetic nature of real numbers. Rational numbers have finite continued fraction expansions. Quadratic irrationals like sim2 have eventually periodic expansions, and transcendental numbers like pi have continued fractions with no discernible pattern. The distribution of partial quotients in these expansions connects to many areas of number theory, including Diophantine approximation, ergodic theory, and even chaos theory. As our mathematical journey draws toward its conclusion, let's take a moment to reflect on the extraordinary path we've traveled together tonight. We began with a simple curiosity about plotting prime numbers in polar coordinates and discovered connections to some of the deepest theorems in number theory. We've seen how rational approximations to pi create beautiful visual patterns, how Euler's totient function counts the ways that primes can distribute themselves, and how Dirichlet's theorem guarantees mathematical democracy and prime distribution. We've explored the historical development of these ideas, From ancient Greek investigations of prime numbers to medieval Chinese calculations of pi to 19th century breakthroughs in complex analysis, we've seen how visual thinking and mathematical visualization have played crucial roles in mathematical discovery throughout history, and how modern computer graphics continue this ancient tradition of using visual representations to illuminate abstract mathematical structures. We've considered the cognitive and aesthetic dimensions of mathematical pattern recognition, exploring how our minds process and appreciate mathematical beauty. We've examined connections between prime spirals and other areas of mathematics, from rational approximation theory to Fibonacci sequences to the broader study of order and chaos in complex systems. Throughout this journey, we've seen repeatedly how mathematics reveals unexpected connections between seemingly unrelated ideas. The patterns we've explored tonight are beautiful not just as visual phenomena, but as expressions of profound mathematical truths. The spiral arms that emerge from apparent chaos reflect the deep organizational principles that govern prime distribution. The systematic gaps in these patterns encode information about arithmetic progressions and residue classes. The transformation from spirals to straight lines illustrates the power of exceptional rational approximations to fundamental constants. Most importantly, we've experienced the deep joy that comes from understanding mathematical beauty. The patterns we've explored reveal the elegant mathematical structures that underlie the apparent complexity of the number system. They show us that even the most seemingly chaotic mathematical objects often hide profound organizational principles that become visible when we learn to look at them from the right perspective. The story of the prime spirals reminds us that mathematics is ultimately about pattern recognition and the search for hidden order within apparent chaos. Whether we're analyzing the distribution of prime numbers, studying the motion of planets, modeling the behavior of complex systems, or simply appreciating the aesthetic beauty of mathematical relationships, we're always engaged in the fundamental human quest to find simple principles that explain complex phenomena. As you prepare for sleep tonight, perhaps you'll carry with you some sense of the mathematical wonder we've explored together. The next time you see a spiral galaxy in a nature documentary, notice the regular spacing of fence posts along a country road, or observe the geometric patterns in a piece of architecture. You might remember that similar structures emerge throughout mathematics, from the distribution of prime numbers to the rational approximations of fundamental constants to the beautiful theorems that connect discrete and continuous mathematics. In the quiet moments before sleep, when the day's concerns fade into the background, there's something deeply peaceful about contemplating these eternal mathematical truths. Prime numbers have been distributing themselves among arithmetic progressions in exactly the same way for billions of years, long before humans existed to notice the patterns. They'll continue to follow Dirichlet's theorem long after our civilization has faded into history. Rational approximations to pi will retain their precision, Euler's totient function will continue to count residue classes, and the beautiful spiral patterns will persist in their mathematical perfection. There's a profound comfort in this mathematical permanence, in knowing that some truths transcend the temporary concerns of daily life. The mathematical structures we've explored tonight exist in a realm beyond time and change, where beauty and truth converge in patterns of perfect logical necessity. These patterns connect us to the deepest structures of reality, reminding us that we live in a universe where chaos and order, randomness and pattern, complexity and simplicity exist in perfect mathematical harmony. The spirals we've explored represent a small piece of this eternal mathematical reality. They remind us that beauty and order exist at the deepest levels of mathematical truth, and that human curiosity and creativity can uncover these hidden treasures through patient investigation and playful experimentation. Whether we're professional mathematicians or simply curious individuals who enjoy thinking about patterns and relationships, we all have the capacity to participate in this great ongoing conversation about the nature of mathematical reality. So as your eyes grow heavy and the mathematical patterns fade into the gentle chaos of dreams, rest assured that the prime numbers will continue their ancient dance among the arithmetic progressions, creating spirals and rays with the same mathematical precision they've maintained since the beginning of time. The theorems we've discussed tonight will still be true when you wake tomorrow, ready to inspire new discoveries and new moments of mathematical wonder. The rational approximations to pi will retain their remarkable precision, creating spiral patterns so tight they appear as straight lines radiating toward infinity. Euler's totient function will continue to count the residue classes that can contain prime numbers, ensuring that exactly the right number of spiral arms remain visible in each prime plot. Direchlet's theorem will guarantee that primes distribute themselves democratically among all available arithmetic progressions, maintaining the mathematical balance that creates such beautiful patterns. Sweet dreams, and may your sleep be filled with the same elegant patterns that govern the distribution of prime numbers throughout the infinite expanse of mathematical space. The spirals await your return whenever you're ready to explore them again, unchanged and eternal, beautiful expressions of the mathematical order that underlies all of existence. In your dreams tonight, perhaps you'll see spirals within spirals, patterns within patterns, each one revealing new layers of mathematical beauty and truth. And with that gentle thought, our mathematical journey comes to its close. The prime numbers continue their eternal spiral dance through the coordinate plane. The rational approximations to pi maintain their remarkable precision across the centuries, and Direchlet's theorem ensures that mathematical democracy prevails in the distribution of primes among arithmetic progressions. These profound truths will be waiting for us whenever we choose to return to them, patient and eternal as mathematics itself. Rest well, fellow travelers in the realm of numbers and patterns. Until we meet again in the land of mathematical wonder, may your dreams be filled with spirals, symmetries, and the quiet satisfaction that comes from understanding the hidden order within apparent chaos. The universe of mathematical truth extends infinitely in all directions, and there will always be new patterns to discover, new connections to explore, and new moments of insight to illuminate the elegant structures that govern the behavior of numbers. Good night, and may the mathematical harmony we've explored together bring you peace as you drift into the restorative embrace of sleep. The prime spirals will continue their cosmic dance through the coordinate plane, weaving patterns of such beauty and precision that they connect the most abstract realms of mathematical thought with the deepest structures of reality itself. In the morning, they'll still be there, waiting patiently for the next curious mind to discover their secrets.